Okay, this is the first part of the video for lesson 1-2, measuring segments, and this will contain the first 5 examples 1 through 5. In this video, you'll learn how to measure various line segments in different contexts using several definitions and postulates from geometry. And in the second part of the video, you'll learn what's required to perform simple geometric constructions and how to make those constructions. So let's begin. Example 1. In this example, you will use the Ruler Postulate. Study the diagram of the number line below. What is the length of ST? We have point S here, point T here. They create a line segment along here, along the number line. And we want to know the distance between those 2 points. Well, to do this on any number line that has coordinates, we can use the Ruler Postulate. So by the Ruler Postulate, we have the length of ST equals the absolute value of the difference between those 2 endpoints' coordinates, S and T. You can also write it the absolute value of T minus S. It doesn't matter. So the length of ST is equal to the absolute value of the coordinate for S, which is -4, minus the coordinate for T, which is 8. So the length of ST is equal to the absolute value of -4 minus 8 is -12. So the length of ST is the absolute value of -12, which is 12 units. So the length of ST is 12 units from here to here. Example 2. In this example, you will use the segment addition postulate. The reason why we know we're going to use the segment addition postulate is because most of the time when you have a segment that's cut up with smaller segments in between, odds are you're going to use the segment addition postulate in some way or form. So by the segment addition postulate, and the segment addition postulate says that we take each of the smaller segments and add them together. So the length of EF plus, which we don't know, plus the length of FG should equal the length of the entire segment EG. At this point, after using the segment addition postulate, we substitute in the values that we know. The length of EF we don't know, so we're going to keep it written as EF, plus the length of FG is 13, equals the length of EG was given as 48. From Algebra 1, this is a simple equation. We then subtract 13 from both sides of the equation, and we get the length of EF is 35, or 35 units long. So this would be 35 units long. Example 3. In this example, you will use the segment addition postulate again. And again, we have one long segment, and it's cut up into at least 2 smaller segments. So by the segment addition postulate, we take the first part of the long segment, EF, or the length of EF, we add to it the length of the other segment, FG, and we get the length of the entire segment, EG. We do this to answer the question. They told us that if EG, the length of EG is 59, so this whole segment is 59, what are the lengths of EF and FG? Well, EF right now is an algebraic expression, and so is FG. So we need to find the value of X first, and then we can find the actual numerical lengths of EF and FG. So Substituting in the values we have for EF, the length of EF is AX minus 14, plus the length of FG, which is 4X plus 1, equals the length of EG, which they gave us was 59. We can solve this equation using Algebra 1, drop the parentheses, and combine like terms on the left side of the equation. 8x plus 4x is 12x, minus 14 plus 1 is minus 13, equals 59. At this point, we add 13 to both sides, and we get 12x equals 72. Then we divide both sides by 12, and we get x equals 6. Now the problem asks us to find the length of EF and the length of FG, and so now we take those algebraic expressions and substitute in the value for x. So the first one, EF, the length of EF was 8x minus 14. Substituting in x equals 6, we have 8 times 6 minus 14, which is 48 minus 14, which gives us 34. So the length of EF is 34 units long. Then for the length of FG, we had 4x minus or plus 1. We substitute in x equals 6, and we get 4 times x, which is 6, minus plus 1, equals 24 plus 1, which is 25. So FG is 25 units long. You can check your work by adding 34 and 25, and you should get 59. In example 4, we will be using the Ruler Postulate and the definition of congruent segments. It asks, are segments AC and BD congruent to each other? So AC and BD. The first thing we need to do is use the Ruler Postulate to determine if the lengths of those two segments are indeed the same length. So by the Ruler Postulate, we're going to find AC, or the length of AC. That's the absolute value of the difference of whatever coordinate at A minus whatever coordinate at C. So the length of AC is the absolute value of the coordinate at A, which is -2, minus the coordinate at C, which is 5. So the length of AC is equal to the absolute value of -2 minus 5 is -7. So the length of AC is the absolute value of -7, which is just 7. Then we do it again for BD. Use the Ruler Postulate. The length of BD is the absolute value of endpoint B minus endpoint D. So the length of BD is equal to the absolute value of B, which is at 3, minus the coordinate for D, which is at 10. So the length of BD is equal to the absolute value of 3 minus 10 is -7. So the length of BD is the absolute value of 7, which again is 7. Now, since AC and BD are equal, by the segment addition, the segment congruency definition, or the definition of congruent segments, then since the lengths are the same, then segment AC and segment BD must be congruent to each other, same size, same shape. So yes, they are the same. In example 5, we will be using the definition of midpoint. In example 5 it says segment AB has its endpoints at -4 and 9 on this number line. What is the coordinate of its midpoint? To find the midpoint of a simple line segment, we take the endpoints, or the coordinates of the endpoints, add them together and divide by 2. This is basically finding the average or mean between those two endpoints. So, by the definition of midpoint, the midpoint of segment AB will be equal to the endpoint at A, which is -4, plus the endpoint, or the coordinate of B, which is at 9, divided by 2. So the midpoint of AB, -4 plus 9, is 5/2, or 5/2, or 2.5, or 2.5. Any one of those answers is acceptable. Let's check it out and see if it looks like the midpoint. Let's plot 2.5. Start at 0, go to the right 2, and this is 3 right here. 2.5 would be right here. And if you'll look, it sure does look like the midpoint, and it is. Examples 6, 7, 8, and 9 will be on the second part of this video.